Welcome to a lesson on quadratic, maximum, and minimum word problems. So we're going to start off with example 1a, and I'm going to follow up with an example 1b, where we compare the two questions after that. Okay? So example 1a, a farmer has a rectangular lot that is bound by one side by a river, and on the other three sides by a total of 80 meters of fencing. Determine the dimensions of the largest possible lot. So the first thing I'm going to do, when it's a question that we can actually draw, I'm going to draw it so I can understand what's going on. So I saw that there was a river here. So I'm going to put the river in blue and draw a little river here. And label it. Okay. There's a rectangular lot that is bound by one side, and the rectangular lot has three sides. Okay, so I'm going to draw my rectangular lot right here. It's bounded by three sides, okay. And they said it has 80 meters of fencing. That means this and this and this is a fence, and the total is 80 meters. And the mathematical quantity of what that represents is perimeter. So really, this perimeter is 80 meters in total. And I know this perimeter is made up by a width here, and a length, and another width here. Okay, so the perimeter is 80, and we also know that the perimeter is two widths and a length, which gives us 80. So now it says determine the dimensions of the largest possible lot. So what comes to mind when you're talking about the largest possible lot, what quantity comes to mind? And the quantity that comes to mind for me is the area. So what is the maximum amount of area that you can enclose using these 80 meters of fencing? Okay, and so what we're going to do is, I know now they want to find the maximum area. So area, I'm going to write this down. The area of this rectangular lot that can be that's being enclosed is length times width. And here I need to find the maximum area. And usually when we're trying to find the maximum of something, we usually have a relation or an equation with only two variables. Right now we have three variables. And so this is something we haven't seen before. We have to simplify it and so that it only has two variables, a relation like y and x. So here I'm going to take a look at this. This is equation. I'm going to call this equation number 1, and then call this equation number 2. And I'm going to substitute 1 into 2. That's what we're going to do here. Or actually, we can't substitute 1 into 2 just yet. I'm going to isolate for either L or W and then substitute it into here to get rid of one of the variables. Simplify it. So which one's easier to isolate for, W or L? To me, I can see that this has no coefficient of 1, this has a coefficient of 2. This is going to be easier to isolate for, and there's going to be no fractions when I isolate for it. So I'm going to isolate for L, and that means I'm going to get rid of this positive 2W. So what's the opposite of positive 2W? I'm going to subtract 2W from both sides. And now I'm going to substitute this into here. So maybe I should call this this I'm going to call equation number 1. I'm going to go over here, sub equation 1 into number 2. So here's number 2, A equals LW. And now I'm going to replace L with this expression, 80 minus 2W. So in brackets here, I'm going to write this in a different color, 80 minus 2W. And I'm also going to have this W here. So I've replaced L with 80 minus 2W. There's also another W on the outside, which is the width here. And so now, I don't know if you guys recognize this, but this is a very important point. This, oopsies, it's supposed to be a highlighter. This is a quadratic. If you saw this with a y and an x, so y equals 80 minus 2x, close bracket with another x here, you would see this as a quadratic that is in factored form. And that's in fact what this is. So really, I can actually draw this out on a graph to understand what's going on here. Instead of A, instead of y, we have an a. So my dependent variable is area. The area depends on what the width of our fencing we choose to be. And so they're asking us to find the maximum, the largest possible lot. This really means the maximum area. So in order to find the maximum of something, of a quadratic, what part of the quadratic are we looking for? We're trying to find the vertex here. Okay, so this is a very important part to realize that this is a quadratic. I'm going to put this in. This is a quadratic. Quadratic in factored form. Okay? So you have to understand that this is a quadratic in factored form. And if it's in factored form, the easiest way to find that maximum vertex, it is to find the x-intercepts, or in this case, the w-intercepts. So to find the w-intercepts, you set a to be 0 or y to be 0. Oops, we should change color here. Set a equals 0 to find w-intercept. Okay, so we're going to set this equal to 0. And now, when this is equal to 0, when we have a factored expression equal to 0, we can easily separate this into two linears equations where they equal to 0. And so now we can solve for w. So the opposite of plus 80 is minus 80. And we divide both sides by -2, and this becomes positive 40. And so we have found, and this is an answer already, what we have found is at what point is the area 0? When is this rectangle have an area of 0? Well, this rectangle has an area of 0 when the width is 40. Let's think about that for a second. If the width here was 40 and this was also 40, and the total perimeter is 80, we're not going to have any more fencing for the length, which now we won't have an ability to enclose this rectangle because all our fencing is here, 40 and 40 here, so we're going to have no area, which makes sense, right? That's what we found here. And likewise over here, if our width is 0, so we have a width of 0 here and a width of 0 here, so that means there's no fencing here, no fencing here, we just have 80 meters of fencing along here. It's just straight, and we're not enclosing any area, so we're going to have an area of 0. So mathematically, what we found makes sense. We found out that the area is 0 when the width is 0, when we have no width, and the area is also 0 when the width is 40. All right, but this is not what they're asking us to find. They're asking us to find the maximum. And we know that the maximum occurs in the middle between these two the w-intercepts. So we can find the average width, which is also known as the axis of symmetry for that parabola. So we're going to average out these two numbers, which most of you guys can do in your head. So 0 plus 40 divided by 2 is going to be 20 meters. So this is when the maximum of this parabola occurs, at 20. So they want us to find the dimensions. We already halfway found our answer now. We have 20 and 20. We just need to find L. And luckily, we actually have an expression that represents L. Or most of you guys can do it in your head. If this is 20 and this is 20 and there's 80 meters of fencing, how much fencing will be left over for the length? You can do it in your head, but I'm going to be a little bit more rigorous and show how we calculated it. So I'm going to write here sub W equals 20 into equation number 1. So here's equation number 1, which is L equals 80 minus 2 and W. Oops. 2 times, got the 2. Okay. And 80 minus 2 widths, it's going to be 40 meters in total, which gives us 40 meters of fencing left for the length. And now we can write our therefore statement because we've answered the question. The dimensions that would maximize area is 40 meters by 20 meters. And that's it. Okay. So how did we start? We started by translating this English word problem into a picture so we can understand what's going on. I understood that this 80 meters of fencing represented perimeter, and I understood that they're trying to find out that this was the largest possible lot. So what we were able to do is, if this is the largest possible lot, that represents an area. We have 2 equations right now. And in this second equation here, normally there should be only 2 equations, 2 variables in order to find the relation between the 2 variables. That's what we've been working with. So we use the other equation to substitute into this equation to simplify into it, which is what we did here. And so now we took a look at this. Ooh, there's only 2 variables now. And it's just like it's y and x. This is a quadratic in factored form. In order to find the maximum, we knew we were to find a vertex. And to find that vertex, we know we have to find the x-intercepts or the w-intercepts by substituting a equals 0 and solving for each of these separately, averaging it out, and then finding the length by substituting back into equation 1. Okay. Please go on to the next video to see what example 1b is going to be like. It's going to be much shorter.